Welcome to tutorial 18 on differentiation rates of change. I'm aware you've done quite a lot of calculus in other modules, so I'm not spending a huge amount of time on calculus. Let's start with an example. So it's a projectile. A stone is thrown vertically upwards. And has the following trajectory. Let's say the height is equal to a quadratic. And we're going to ask, what's its initial position velocity? So we're going to ask a question. Initial velocity and initial position. And what about its acceleration? And maybe also, where does it land? As well as its velocity. So if you sketch this quadratic, it looks something like this. So we have some time, and then we have height. We know that this can be written by completing the square, going way back to the first part of the semester. So the quadratic looks at time 1, it hits its maximum. And if you could also find the roots. But it's going to look something like this. If you plug in t equals 0, you get 5. So here is h0. It looks something like this. And so you have some initial velocity, which is its slope here. And so on. So let's answer these problems. So the velocity in general is the derivative with respect to time. So here is the change in h over the change in time. Let's say everything was in meters and seconds. So here, if we take the derivative with respect to t, we get minus 10t plus 10, and that immediately implies that v0 is 10 meters per second. Notice that the units are as division. I should say that immediately we had previously that h of 0 is evaluation, and we already said that that's 5. And the acceleration is the change in the velocity with respect to time, and is also, therefore, the double change in the position with respect to time, and that's equal to minus 10 meters per second squared. And this turns out to be a constant, so the acceleration times 0 is also the acceleration at any time. So as a remark, so for general rates of change, the idea is that differentiation is the approximation, is the linear approximation. So suppose I have a function which is actually straight, so it's actually linear, then the rate of change at any time is the same. So if your function is y is mx plus c, you well know that the rate of change is this constant, as above in the acceleration case. But as we're going to do things which for non-constant rates, and later on in the integration section we'll also do non-constant acceleration. So look forward to that. But for general functions, so suppose here's some kind of cubic, and what we want is the slope. This is the linear approximation x naught, and it's approximated by what? It's approximated by a little change. It's approximated by this change in f, or the change in y. Let's say so there's y. So it's approximated by the change in y over the change in x. So dy by dx is the limit as this little change in x tends to 0 of the change in y over the change in x. So from first principles, we show that d by dx of x squared is equal to 2x. Actually, in class I did the case where we did x to the n, but we'll see. Let's just see it for the quadratic case. So the change in y, which is x squared, so it's your initial value, as you clarify for the quadratic. Let's say that your initial point is at x naught, so that we're finding the approximation near here. So suppose we change a little bit by delta x. And so this is x naught plus delta x all squared. But because it's the change in y, we want to subtract off our initial value, which is just x naught squared. And so that's equal to, well, you can expand the quadratic and cancel the term. The good thing is that the initial values will always change. You're always just measuring the change in y. Then the relative change, so the slope, is equal to, well, the above thing over delta x. And so one of the delta x is cancelled. And this tends to 2x naught as delta x goes to 0. And that's no surprise, right? We know that the slope of a quadratic of x squared at a point is 2x. And we clarified that the point is x naught. So what are some formulas you might want to know? So we know, quadratic derivatives, d by dx of x to the n is equal to n times x to n minus 1. We know if you take two functions, then the derivative of the sum is the sum of the derivatives. And that if you have a constant scalar, lambda times a function, this is just the scalar times the derivative. I know you'll also have done the chain rule and the product rules in other classes. We're not going to dwell on those in this one. In class I explained to some students the geometric origins of these things. And we also need to know that d by dx of sine x is cos, and d by dx of cos x is minus sine x. The idea is that if you actually draw a very nice, accurate looking trig, better than I can draw in real time, it looks something like this. Here's 2 pi, there's 1, and in fact, yes indeed, say the derivative of sine at this point is slope 1. But notice that there are special points, e.g. pi by 2 and 3 pi by 2, where the slope is constant. And that brings us to our last definition we need to know, is that a critical point which you may also know as a stationary point, is a point x0 and the value of the function at that point, f of x0, such that the derivative is 0, or that the slope is 0 there. So that df by dx at x0 is equal to 0.